Good evening, everybody, and welcome to this hybrid lecture put on by the Audio Engineering Society Cambridge Regional Section. It's my privilege to introduce Mr. Christian Cotton. He is a research and development engineer at Meridian Audio, where I also work. And Chris studied at the University of York, where he received a Master's in Engineering. And studied and did his master's in room acoustic modeling techniques, and has publications in spatial and binaural audio. And today he's going to be talking to us about auditory source width of stereo signals. Please can everybody leave questions to the end and use the Q&A feature for people participating in Zoom. And I hope everybody enjoys the talk. Thanks very much. Take it away, Chris.
Thank you, Ethan. Good evening. Thank you very much for coming, and for everyone on Zoom that has tuned in. So yeah, I'm going to be talking about measurement and control of auditory source width of stereo signals. But what does that mean exactly? So what we're talking about is with auditory source width, we're talking about the lateral extent of the perceived phantom image created by two loudspeakers in stereophony. And we're looking at objective numerical quantities which we can use to describe and manipulate how we perceive that lateral extent of that of the phantom image. So in this talk, I'm going to just take a step back first and talk about ASW in a general context as an element of spatial impression of a sonic reproduction system, and then go on to talk a little bit more about auditory source width. Then we'll look at how we can control auditory source width using cross-correlation techniques, and then we can listen to some sound examples. And then we'll look at how we would measure auditory source width using energy-based metrics, cross-correlation-based metrics. And then we'll look at a novel approach that myself and my colleagues at Meridian have been, that's been a subject of my research with my colleagues at Meridian over the last 18 months. So, first of all, spatial impression. The spatial impression of a audio reproduction system, it's the audition sensation of the listening environment within that system. It's characterized by the initial reflections. So when our stimulus is injected into our listening environment, the initial reflections that we hear describe to us how we perceive the space in all directions and throughout time. And our spatial impression is dictated by arrival time and direction, amplitude of reflections, and also their frequency response to their spectra. We can attain a general assessment of the spatial impression using simple room impulse responses. So we could, using something like an exponential sine sweep, we can get room impulse responses and extract certain acoustic properties like the lateral energy fraction, which we'll talk about later. But we can attain a perceptual assessment of a reproduction system's spatial impression using head-related impulse responses, which means taking a measure of the reproduction system using a binaural dummy head microphone, and that way we can and then from that information, from those head-related impulse responses, we can extract binaural cues, so interaural level differences, interaural time differences, or phase differences. And then we can also use that information to evaluate the subjective listening qualities. Things like listener envelopment, which describes the sensation of being surrounded by sound on on a horizontal plane, or listener engulfment, or LEG, which is the sensation of having sound above you and around you, so in a vertical plane. And then lastly, there's ASW, or auditory source width, which is what I'm going to be talking about today. So, auditory or apparent source width, ASW, as I said at the beginning, it's the perceived lateral extent of the sound stage created by an audio reproduction system or an audio production system. There are many examples of that. Obviously, we're just focusing on stereo today, but such an audio reproduction system could be a multi-channel loudspeaker array in a vehicle cabin, or a stereophonic loudspeaker pair in a listening room like we have today. It could be something like an ensemble performance in a theatre, or it could be something as simple as headphone playback. And we can control ASW in two domains. The first one being the physical domain. So we can control ASW at a physical level by varying the placement of our loudspeakers. So we could increase the distance between our loudspeakers, which improves our stereo image, makes it wider. We could also move our loudspeakers throughout an arc, which enhances and alters the spatial impression. And then we can also use room acoustics. So room acoustics, as we'll see in a second, room acoustics enhance spatial impression, enhance ASW, and if we want to control ASW passively, that is without any processing, we can consider how the acoustic properties of our listening environment are being perceived at the listener. And then the second modality for controlling ASW is via the signal processing domain, through varying the interchannel cross-correlation function, or ICCC, of the input signals. So ICCC is the maximum absolute of the intercross correlation function, which is a measure of the similarity between our left channel and our right channel. That produces a value between 0 and 1, which becomes our ICCC. It's important to note that the ICCF, our cross-correlation function, can yield negative values, and that has some perceptual implications. But for the vast majority of ASW applications, ICCC is traditionally viewed as a value between 0 and 1. So we can vary ICCC in a number of ways. We can use simple comb filters. We can use filters such as like Lauridsen decorrelators, raised cosine all-pass filter architectures like the one on the figure on the screen, or even relative phase shift operations. We can use them and tune them to change our ICCC and therefore our ASW. We can tune them to a desired ASW and impression spaciousness. So at this point, we can listen to some sound examples. Hopefully this comes through on Zoom, but the attendees in the room should hopefully definitely hear this as well. So we'll start with an ICCC of 1. That means that our input signals are totally correlated. They're as similar as they can be. They are essentially the same. So there is no added spatial impression into our system. We just have a simple mono input. Okay, and then an ICC of 0.8. So the lower our interchannel cross-correlation coefficient, the more decorrelated the signals are becoming, so the greater the impression of width becomes. Now at 0.8, it's especially you'd notice this the most, those of you that are sat right in the middle, which you guys are, you'll notice a very small, you'll notice the image start to become more diffuse, but as we listen to the other sound examples, you'll hear it get much wider. So here's 0.8, and then for each sound example, I'll just play a little bit of our reference, our ICCC equals 1, just to refresh your ears. There we go. So that was a ICCC of 0.8, or in a direct thinking about a phase difference that's approximately a 45-degree phase difference. So I'll just play our reference again, and then we'll move on to the third sound example. Okay, so this is a interchannel cross correlation coefficient of 0.67, so roughly 60 degrees of phase shift. And our reference again. Now ICCC equals 0.45, so we're just over 90 degrees of phase shift here. Our reference again. And ICCC equals 0.28. Our reference once more. And our lowest interchannel cross correlation 0.1. Okay, so those were some sound examples. Also, I misspoke throughout that. My apologies. So our lowest ICCC ICCC equals 0.1. That is approaching 90 degrees. and our ICCC of 0.45, that was around 45 degrees. And also apologies for members in here and online who aren't a fan of Muse. So that was those are some sound examples of just one way that we can directly change ICCC. There are other ways, like using a relative phase shift approach, which is much more an offline process and much more involved process. But in terms of measuring ASW, we have to first consider a measurement process. So we might want to use impulse responses recorded via exponential sine sweeps to get either, like I said, room impulse responses or binaural room impulse responses or head-related impulse responses if we were in anechoic conditions. Although we might want to use pink noise bursts to get a perceptual capture of the spectra of our auditory system, or we might even want to use speech if we're only concerned about, for example, if we were only interested in making the vocal in a piece of music wider, we might just want to use speech. And then, like I alluded to just then, the receiver modality. So we may want to capture a binaural recording. We might just want to capture a stereo recording. And then there's what we actually want to how we actually want to calculate ASW. So there are I said at the beginning that we're going to look at energy-based metrics of ASW, correlation-based metrics, which we just briefly touched on, and a novel approach. So looking first at an energy-based metric, this is quite ubiquitous among the literature, especially for spatial impression. We have the early lateral energy fraction, or LFE. Early, the E subscript stands for early, and that corresponds to the first 80 milliseconds of a response. So early, the LFE is captured using a omnidirectional microphone, excuse me, and a figure of 8 microphone, and it's simply just the ratio of the sound from lateral directions to the sound energy from all directions, and that's most useful in larger reverberant listening environments. And then there is, and then looking at cross-correlation based metrics again. So at our input level, we had inter-channel cross-correlation. At our output level, at our measuring, when we're measuring at the listener, we have inter-oral cross-correlation coefficient, or specifically early inter-oral cross-correlation. Again, early 0 to 80 milliseconds, just considers the initial reflections. So, and again, like ICCC, IACC is the maximum absolute value of the inter-oral cross-correlation function, which is, again, just a measure of the similarity between your left and right ear signals. But it's defined, it's only valid between the phase shifts tau of plus or minus 1 millisecond, which corresponds to roughly the maximum inter-oral time delay as a result of head shadowing. Just like ICCC, it produces a value between 0 and 1. And it's often band averaged over 500 hertz to 2 kilohertz. This is because, as we'll see a little bit later, human perception of ASW is actually an inherently band limited process. And then we have a more novel approach. So this is the inter-oral thresholded level distribution, or ITLD. This is the result of a research project at Meridian looking into objective metrics of spatial audio, of spatial spatial listening qualities, and it's essentially a hybridized approach. It uses both. It's an energy-based metric, but it also relies on time domain congruence between the left and right ear signals, and it employs, most importantly, a simple model of the human auditory system, specifically the function of the cochlear inner hair cells. So to speak a little bit more on that, essentially we take measurements of our stereo loudspeaker pair in a room with a binaural dummy head microphone. So we have a left ear signal, and we have a right ear signal. Then we apply a low pass filter with a cutoff frequency of 1000 Hertz and a filter order of 6. And then we half wave rectify our signal, which gives us our lambda L and lambda R of T in our equation. And then we simply multiply them together and take the sum of their products. Again, like ICCC, like IACC, and like the LFE, it also produces a value between 0 and 1. However, ITLD accommodates for negatively correlated ear signals. So in the sound examples that you heard, all those sound examples, they were positively decorrelated. It's going to get a little bit messy here, but if you decorrelate your input signals beyond 90 degrees, they start to become negatively correlated, and they become increasingly negatively decorrelated till you get to 180 degrees of phase shift, and you would have a ICCF maximum value of -1. But when you use a metric like IACC, you're getting rid of that information, and the negative sign in the cross correlation actually has some perceptual information. It actually tells us that the image becomes so wide that it starts to be perceived as two distinct lateral images. But that information, like I said, is thrown away when you use other metrics. But it's included in ITLD. So we'll have a look at the difference between IACC and ITLD in the next slide. But yeah, it is a normalized measure of the temporal congruence of the left and right binaural head signals. So yeah, this slide just shows the difference between IACC and ITLD, both in anechoic and in an anechoic chamber and in a reverberant listening room, using a stereo pair of loudspeakers with a binaural head in the middle. So we can see that the top two figures, IACC, it has this sort of W shape, and that's what I was saying about the IACC being throwing away some of the information. It's symmetrical about it's symmetrical about 0. So this x-axis here, this delta phi, is the amount of phase shift in radians. So over here you have basically a input decorrelation of -1, and then you go up to +1 here, and we have 0 in the middle. So we can see that it's throwing away all the it's throwing away all the information. They're essentially mirrored. Whereas when we look at ITLD, we see that although it is symmetrical about 0, it's not symmetrical about pi/2. Similarly, like IACC is, which means that we've got full representation for all possible binaural ear signal correlations. So just a comparison, just a summary of ASW metrics before we talk about some limitations when measuring ASW. So lateral energy fraction isn't a binaural quantity. It's an energy-based metric. It's practical and it's effective when we can in highly reverberant environments, and when we can adjust the acoustics easily if we actually want to control if we actually want control over ASW. But because one of its big disadvantages is that the direct sound component is omitted from the lateral energy sum, which can mean in less reverberant spaces like a room such as this, there it's typically less perceptually valid. Then we've got the early interoral cross-correlation coefficient, IECCE. It's a binaural quantity. It's correlation based. It's had a well-documented strong perceptual relationship for positively decorrelated signals. It's computationally very inexpensive, however, it does suffer from poor off-axis performance, which we'll see in our next slide. And it's unreliable for negatively correlated signals, like I've said. And then finally, ITLD. So yes, it's a binaural quantity. Its basis is a mix of energy and time domain congruence. It has a full representation of all possible signal decorrelation, and we showed in our last paper for ITLD that it actually has a very strong perceptual relationship for pink noise sources. It does also unfortunately have poor off-axis performance. And speaking of off-axis performance, so you'll all know that when we listen to stereo content, there is a sweet spot in our stereo loudspeaker setup where we get the full benefit of a stereo system. And as we start to move to the side, we see we're not able to localize content as effectively as we can when we're in the middle, and our image starts to collapse and so on. And that is actually reflected in the controllability of ASW. So the figure that we can see on the slide, we can see that the more we shift ourselves from the central listening position, so basically essentially more than 30 centimeters, ASW becomes largely uncontrollable, and so we have to really consider how much we're going to allow to like if we want to tune ASW for multiple listening positions, we have to think about how different positions are going to be affected by a certain input decorrelation, for example. And yes, like I said, ASW perception in the human auditory system is a band-limited process. So the simple model of the human auditory system, that I mentioned previously, what happens essentially is that we have sound waves disturb cochlear fluid, and we have hair cells inside the cochlea, which when the fluid moves, the hair cells. The hair cells trigger the transduction of electric signals in the auditory nerve. these signals exhibit phase locking above approximately 2 kilohertz, and what that means is they're unable to resolve the fine structure of high frequencies. So typically, we see that the upper limit for a lot of ASW metrics is 2 kilohertz, and we also see a lower limit of 500 hertz, which is to do with looking at wavelength and the dimensions of the head. Before frequencies below 500 hertz, the ear isn't able to accurately localize those frequencies. So in summary, auditory source width is the perceived lateral extent of the sonic image. In our case, the phantom image produced by a stereo loudspeaker setup. The ASW stereo signals can be controlled by varying the interchannel cross-correlation function coefficient. ASW can be measured using various approaches, including the established energy-based and cross-correlation-based metrics, so our lateral energy fraction and our interaural cross-correlation coefficient, as well as a novel approach which employs a simple model of the human auditory system, or ITLD. Thank you very much. There's a list of references there for the sources that I've used in this. Thank you very much. Questions?
Right, thank you, Chris, for that talk on ASW and interaural threshold level distribution. So I've got a few questions to ask and just kind of get your thoughts on. So you mentioned LFE as an exemplar energy-based metric. Are there any energy-based metrics aside from interaural threshold level distribution that are able to be derived from binaural recordings?
So there is there's a, I believe it's called an energy vector, exists in the literature. I believe it's from quite an old paper, but generally what you see from binaural, what you see used as sort of the state of the art for binaural quantities is the cross correlation based metrics.
I suppose that's an advantage of ITLD, though, to combine based values.
Yeah.
Okay, cool. Have you thought about the extension of ITLD to measuring multi-channel audio, i.e., surround sound formats?
Yes. It's definitely. It's a very interesting. It's a very interesting proposition, because so far all the research that's been done with ITLD has just been with stereo content. There's been a little bit of research using mid-side decomposition, which ITLD is shown to be effective for characterizing changes in ASW according to different depths of mid-side decomposition. But yeah, adding a greater number of channels with surround channels, or maybe even heights, it will be very interesting to see how the metric behaves, especially in tricky conditions like asymmetric loudspeaker placement and stuff like that.
Yeah, well, I suppose it would still hold up as a metric because it is a binaural metric. It's more about, I would imagine, the source content that you drive a system with, and how do you prescribe content that is or isn't wide. I suppose that's a selection of. So that goes, I guess, into the physical domain of selecting certain loudspeakers.
Yeah, and even beyond a sort of from a sort of product perspective, like the raised cosine filters that we listened to earlier, if you wanted like a vocal or something, or in a mix to sound wide, those filters work in that context as well. So
it's really cool. Yeah. Do you think there's any interaction between the physical speaker placement that you mentioned as a method of increasing stereo width, and then digital manipulation of signals to further increase it? Do you think that would?
That's very interesting. I mean, I've got to imagine it would, because I mean, you'd see like whatever your however you would perceive the ASW of your content. So say you used one of those raised cosine filters when you're in the central listening position. You've just got a loudspeaker here, a loudspeaker here. Let's say that they're 4 meters apart. You've got a nice sounding wide image, and then you suddenly you make them 6 meters apart, or you bring them out in an arc. You're going to have however that different placement has affected your binaural cues. That's going to be layered on top of what the filter architecture is going to do as well.
I suppose that you get to kind of a maximum saturation point because things can only be so decorrelated.
Yes, yes, they can.
Or negatively
yeah,
maximally correlated. I guess. So that's an interesting point, that you kind of relate the distance of speakers to what level of ASW or ITLD that you measure. Is there any sort of known relationship between physical units of distance and like the value of either ASW or ITLD that's derived from system measurement?
What physical units of distance in terms of loudspeaker placement?
Yeah, like could you derive?
So
because it's a relative metric, right?
Yes.
Like, it's from 0 to 1. So you can compare two different things and say that's wider than something else.
Yeah.
But is there a relation of how wide it? I suppose you just have to compare it to.
Yeah. Well, I suppose if you if you have a once you have a characterization of a space, a perceptual characterization of space, I suppose the thing to do in terms of ITLD research, because we so far our perceptual validation experiments that we have done, they were performed in a reverberant environment. So the thing to do would be to conduct those experiments in an anechoic environment.
Yeah.
And we get an anechoic representation, an anechoic relationship between ITLD and ASW, and then you'll be able to transfer that across into any environment based on relative ITLD values.
Have you done any listening in anechoic yet for this?
I believe we did right at the start. We haven't done any formal listening tests in anechoic. It's just been in reverberant environments, but it's definitely an important avenue for further research with ITLD.
Excellent. So you spoke earlier about the poor off-axis performance of both ASW and ITLD. What would you expect a good metric to highlight? What would you expect to see if you were to change the lateral offset of a receiver?
Well, what we did actually have a look at how both IACC and ITLD behave when you vary the lateral shift from the central listening position. And what you essentially see is that you essentially see just a flat line. It's for however many different as your source decorrelation decreases, you would expect to see, either like the W trend for IACC or the tapered cosine window for ITLD. What you end up with is just a flat line, because and I think that is whether or not that makes it a bad metric, I don't know, because that is what you're hearing. It's quite tough, but yeah. Because
so then is it a poor quality of it, right?
Yeah. Wow.
Can we actually measure?
Yeah. Well, that's very true. I suppose what would be interesting would be to include a rotation of the head, a rotation of the binaural head in those measurements, as well as a lateral shift. So changing the azimuth angle of a binaural head in congruence with its lateral shift, and see what happens there.
Yeah. I was going to sort of point out as well, actually, with what we were referring to in terms of shifting the lateral position. I imagine you're only going to shift it within the active arc of a loudspeaker, because once you get outside of that active arc, are you even expected to be able to measure source width?
Yeah, I mean, yeah, that's very true. I mean, you're just listening to a strange jumble of diffuse reflections at that point. So yeah, I mean, I imagine, yeah, you would be very much constrained to your at least the distance between your loudspeakers.
Yeah.
And beyond that, yeah, you're just asking for trouble, I suppose.
I've got a question from Victoria here. So thank you for the insightful presentation. I had some difficulty hearing the audio excerpts clearly on here. I think that's because we mic this up with a shotgun microphone, so apologies for that. Could you recommend any papers on the ICCC algorithm that would help me practice implementing it and understanding the differences?
Yes, definitely. So if the the first source you can see here on the screen, so Franz Zotter and Frank Matthias, efficient fan source widening is where the sound examples that we listen to, the raised cosine filter that was used to create those sound examples, which in fact is on this slide here. The full derivation and implementation of that filter, along with a number of other, along with different comb filters, Lauridsen decorrelators, they're all available in that paper. They also give some interesting They also give definitions of different ASW metrics as well. And yeah, it's very good paper. Yeah.
Excellent. Okay, thanks for the recommendation. Do we have any other questions from our in-person audience or from online? Okay, then. I think we can wrap this up then. So thanks very much, Chris, for giving a really insightful presentation on ASW and interval threshold and level distribution. I'd like everybody to thank me again thanking Chris for his insights today. So thanks, Chris. And, thanks everybody for attending in person and online. And I hope to see you at the next hybrid lecture that we do. Thanks very much.